So you're exactly right, it's a sine wave. And that pattern going around a circle produces a sine wave. Mine should have been steeper, but... And then he gets off and walks away.
Oh.
Oh.
Because
that's just stupid. Sorry, I don't want to play the distance from the center of carousel. I wanted this one. So, the graph tells a story. At this point, when the graph is flat for a second, he's not moving towards the camera away. At these points here, are you happy he's moving toward the camera as fast as he'll ever be? It's like the steepest down. And then it gets slightly less steep, less steep, less steep, and he's now moving not towards the camera at all, and then he starts moving away from the camera as he gets steeper. Calculus is all about how steep the graph is at a point. And if we can tell how steep it is at any one point, we can tell quite a lot about the context of what's happening.
Yes? Isn't steep just like a relationship with you, like 2 points?
Yeah, you're right. We do. Do you want to jump to that? We can jump to that. So, for steepness, we need 2 points. We're going to do a very boring textbook example. And it's about Chris going hiking. So this is Chris, he's going hiking. And this shows his elevation hours into his hike. So, he starts a bit flat, there's a steep bit, then he walks, and then at the top, for like 15, 20 minutes, he just walks flat along the top of the mountain, and then he starts coming down. And that's the story of Chris. And we want to find his average rate of elevation from t equals 1 hour to t equals 2.5. And I think they've picked the numbers very carefully. T equals 1 hour, he is 100 meters high. Oh god. 100 meters high. And why is it doing that? Alright, can you guys click 1 hour in? There we go. And 2.5 hours. And we can see that the average rate of change, if we were to rule a line between the two, we can do rise over run. So this is rise over run, or 2.5 take 1 over 250 take 100 is going to be 100, meaning completely reverse those numbers, sorry. Swap those. The rise is the 250 and the 100, and the run is the hours. Don't know why I wrote them the wrong way around, because I knew the answer should be 100. What that means is the units here are important. That is 100 meters per hour. Because if I'd done this right, and I'll correct it now, the hours will have been on the bottom of 2.5 take 1 and 250 take 100 on the top. So our average rate of change is 100 meters per hour, meaning that on average he's climbing 100 meters an hour for those 2 points, between those 2 points in time. And Z's right, you need 2 points to make that happen. Do you want me to do the next one between 3.5 and 6? Yes, exactly the same. So 3.5 is somewhere here, 6 is somewhere here, and the average rate of change is this line, straight line between, and we're expecting a negative now because he's dropping a certain number of meters per hour. So he's dropping 250, so take 250 over 2.5 hours. Perhaps unsurprisingly, then he's dropping 100 meters an hour.
But it's a rate of change, not rate of height increase.
Yeah, I guess change here is change in elevation, which will be rate of height increase.
Okay.
Yeah. All right, so let's say that we don't want to find the slope between 2 points. Because between 2 points assumes a straight line between 2 points. So it's assuming a straight line there. Let's say we want to find how fast he's dropping at the steepest part here, like on that point in particular. And what we're looking at now is finding the slope at a point. And I think I put my notes in slightly the wrong order. So can you just jump over the page until you've got this? If we've got a curve, you guys, since about year 8, will have done rise over run between 2 points. And that would be a slope between those two. What we're looking at today, and this is the core of calculus, is how do we find the slope at 1 point? And the slope at 1 point is drawing a tangent to the curve, meaning it just touches it once at that 1 point. And sometimes we can do this visually if life works out well for us. So go further down this page. If I want to work out the slope when x is minus 1, when x is minus 1, they've drawn a tangent in. The slope of the curve at x is minus 1 is, well, we can do the rise and the run of this tangent. So it rises 1, runs 1. The slope there is 1. And so we're happy with the idea that a curve at a certain point can have a slope. It sounds weird because a slope we used to think of between 2 points, but there can be a slope at a point. Remember that? So slope at a point here is 1. In this case here, when x is 2, the tangent looks like it merges with the line, but it's really just touching it once there. And this tangent runs 1, rises 4, so the slope here is 4. And, that looks like a steep slope. So we can measure the slope at different points on the line. Slope of 1, slope of 4. It's possible here there might be a slope of 0, because it's a horizontal line for a second. Alright, so if we're hunting slopes, can you guys go back to the previous page? Sorry about that out of order. We're going to hunt the slope between 2 different points, and we're going to change those points. So, we're interested in the slope when x equals 1. And we've got this curve, and it's a curve that we've seen lots before. It's the quadratic curve. And we want to know, when x is 1, what is the slope of that tangent? So, what they've suggested we do is we start by finding the slope between x is 1 and x is 2. Alright, so I'm just going to draw a little table here, and we're going to look at when the left hand, or the right hand x rather, when the right x is 2. So the right x is 2, we'd imagine drawing a line from 1 to 2. A line connecting those 2 dots is not a perfect approximation of the tangent. The tangent would be there, touching it once, yeah? But a line connecting 1 and 2 is a good place to start. It's like vaguely the same size. It's not perfect, but it's a good place to start. So we're going to find the slope between these 2 points, 1, 1 and 2, 4. So this is between the points 1, 1 and 2, 4. The slope will be 4 minus 1, rise over run, 4 minus 1 over 2 minus 1 is 3. Yeah? Alright. And then what the textbook says is, if between 1, 1 and 2, 4 is not a very good slope, why do we go between 1, 1 and 1.5? You see how I've moved it, and it's getting closer towards what would be the true tangent, but now I'm here. So we're like dragging this dot back. Alright, so we're looking at 1.5. Then we're going between the point 1, 1 and 1.5, 2.25. And this then becomes 2.25 minus 1 over 1.5 minus 1.
Isn't it just the sum of
The sum,
yeah, the sum of the x1 and x is 3, 2.5, 2.1, 2.01, and 2.001?
I don't think we're adding them, are we?
No, I just mean the average rate of change.
Oh,
You know,
oh, you mean summing the averages here, but to average slopes?
No, I just meant that for like I it's going to be 3, for I it's going to be 2.5, no, 1.5, 3 it's going to be 2.1, 4 it's going to be 2.01, and 5 is going to be 2.001.
Yes.
So, is that just because
Hang on.
that's how...
We're going faster than me, but yeah, hang on, we'll just skip all 1.01, 1.001, and what were your answers? 2.5.
2.1, 2.01, and 2.001.
Yeah. And we can substitute them all into the slope formula and work them out. So what's happening is, we've started with a slope between 1 and 2, and we're dragging this dot back. So we're keeping this on its place, but as we drag it back, and as this dot gets closer and closer and closer to that one, are we happy that our slope gets closer and closer and closer to a number?
Closer to...
Yeah, closer to 2.